Okay, so are you ready? We are going to do full hypothesis testing from start to finish. We're going to learn 3 different approaches to completing a hypothesis test, one of which we've already done, which is the p-value. And that's the method we tend to opt for just because it is a universal way of completing a hypothesis test. But there's also the classical approach, and it's a nice approach, but it has the word classical in it for a reason. And then the other one, the third method is confidence intervals. So that's kind of a useful thing. Now we get to see it in a different light. So let's just go through the procedure and then we're just going to like hammer out some examples. Okay, so here is the method. So first we gotta, read the problem and give it an assumption and a claim. The step one is to determine the null and alternative, right? So no, we're gonna do null and alternative. And then we're gonna go ahead and mark the claim. Just looks off. We're gonna go ahead and mark the claim with like a little C in a circle. And then we're going to determine the type of test and draw a figure. We've already done that. And we have a level of significance alpha, which we've already done, right? And so now the classical approach, the step 4 will be step 4, 5, and 6 are the different approaches. You don't need to do all 3, and we will concentrate mostly on the p-value approach, which is step 5. So the classical approach just says, make sure to get the degrees of freedom n-1 from the t-test, and then we're going to use one prop z-test. So if you're going to use the classical approach, you'll need to do the t-test for a mean and one prop z-test for a proportion. So if we went to our calculator and went to stats and went to test, you're going to see that these are in here. So the t-test is right here, number 2, and the one prop z-test is number 5. Those are the 2 we're going to use the most in this chapter. When we move on to other chapters, we're going to use everything else. Okay, then you're going to determine the critical value, and then you're going to compare the critical value to the with the test statistic and see whether or not we would reject the null. It's the same way. So as the p-value. So if I just drew it here, right, here's the population parameter, whatever that is. So it's a mu or a p. So here would be your t sub alpha, right, or z sub alpha, where this area here is alpha. And then you would determine whether or not that test statistic t or z is in the critical region or not. So the critical region is going to be, let me do a different color, I think that'd be better. The critical region is this shaded region. We have that anyways, right? Like with alpha. And so we just determine whether or not it's in the critical region or not. So if you compare the critical value with the test statistic, if the test statistic lies in the critical region, then we reject the null. So here's t or z, and then we reject. And so you can be, it's just like the p-value, right? So if the p-value is in this, to the right of the alpha, we reject the null. If it's not, we do not reject the null. Right? So it's the same thing, except we're using z-scores and t-scores. In part p-value approach, step 5, it's exactly what we've been doing. I won't go over it. And if you haven't, please watch section 9.4 notes. And then the last one is the confidence interval approach, where recall that the confidence interval estimates the population parameter, right? We had this like margin of error, this MO, right? And we had a lower bound and upper bound. And really in the area in here is the alpha over 2. Remember, we had to split it. Okay, and then so if we do a confidence interval, right, from using the t-interval, just chapter 8 methods, then we find if the confidence interval does not contain the null hypothesis value, the results are statistically significant and we reject the null. So if it's not in here, so meaning if that population parameter is not in here, we reject the null. So as long as this lies in the confidence interval, we do not reject the null. But let's say we had a mean and parameters of a mean and a proportion, and let's say P or mu lies outside the confidence interval given a certain confidence level, right? If it lied outside this interval, then you reject the null. So essentially, if it lives in the tails, you should reject it because the whole point of the confidence interval is being confident that the population parameter lies in there, right? So some students love this because it's like a one-step thing in the calculator and they check it, they compare, oh, boom, and then reject, not reject. So the confidence interval is a nice way of actually doing the hypothesis testing. But in our class, we are going to go ahead and veer towards step 5, which is the p-value approach, only because we're going to use p-value for the rest of the semester in the rest of the chapters. When I'll show in the last example all 3 methods so you have an idea, but then from then on we'll just use p-value. Okay, so let's go ahead and try an example. And then just before we start 9.8 example, just as a copy and paste of the tails, right? So if they're equal, if they say that it's different, remember this one, it said that, oh, it's just different from the population parameter. And then left-tailed was less than, right? And then right tail was more than, and all the synonyms like decreased, increased, or whatever. And then here is the steps in the calculator. And again, if you're given raw data, and we are going to have examples with raw data, you just put them in L1, right? But don't always forget, we always have to do the preliminary. If it's given to us that it's a normal, the data come from an approximately normal distribution population, then we'll be fine. But overall, we always need to keep in the habit of checking those preliminaries. Okay, so let's start with a simple example. The mean throwing distance of a football for Marco, a high school freshman quarterback, is 40 yards. The coach tells Marco to adjust his grip to get more distance. The coach records the distances for 20 throws. For the 20 throws, Marco's mean distance was 45 yards. The coach thought the different grip helped Marco throw farther than 40 yards. Conduct an hypothesis test using the preset and assume the throw distances for footballs are normal. Ooh. So that's a huge thing. So if I went over here to preliminary, the first thing we need to make sure is that sample size 40 is no more than 5% of all. And what would be the population here? Would it be football players? Would it be quarterbacks? And so if we think about it, what does the 40 represent, right? 40 yards, right? Yards. So 5% of all yards that he's thrown on a football field, definitely, because those football fields are pretty huge. So the second part, though, is not worrying about it, because if we assume the throw distances are normal, then we can already make that check mark. The first part, remember, is for independent samples, right? And this one is for normality. So those two are already satisfied. So that's really nice. I think to follow the steps above, the first thing we would do is go ahead and determine the null and alternative hypothesis. So let's go ahead and go to the hypothesis test. And we know it is a mean because they give us the mean. And so therefore, it's not a proportion, right? So we know it's a mean. And so the first thing we want to do is set up that hypothesis. Well, remember the null is status quo. So what was the status quo? It said that he can throw 40 yards. But the coach says, you know, change your grip, throw it a different way. And I think you threw farther. So throwing farther, does that mean there's less yards that Marco threw, or is there more yards to what Marco threw? So more, right? So then we would have to say, and let me go ahead and highlight that, throw farther. That mean is more than 40. And then mark the claim. And so this is the coach's claim. So we'll go ahead and put that C there. The second part is to determine the type of test and draw it, right? So 2 is over here on this figure. So what I would do here is probably just put 40 in the middle. And if it's more than 40, then we know it is a right-tailed test. So if we go up here, right, right-tailed, greater than, more than, and so we're going to go ahead and make that a right-tailed test. So what does that mean? That means that if I drew where alpha is, so over here right-tailed, this is going to be some t sub alpha. Where this is alpha. And alpha is given to us. Let me see, I think that's the next step. So step 3, let's identify the alpha. The alpha is given to us as 0.05. So that means that in the area in this tail is 0.05. So in the p-value approach, this p-value would have to be smaller than 5% in order to reject the null and have enough evidence for Marco's claim, right? So then step 4 in this case will be now the approach, right? So in this particular case, we're going to go ahead and do what we've been doing. We'll just stick to p-value, and then in the next example, I'll do all 3 cases. So to get the p-value, you're going to have to go ahead and go to the t-test in the calculator. So let's go ahead and do that. So you would go to stat, and then go to tests, and then go to t-test, which is number 2. And again, we use the t-test because it's the t distribution. So number 2. So it gives us an option, again, for data and stats. You've seen this before, too, with confidence intervals. So just go to stats because they gave us everything we needed. And so if we go ahead and enter in the mean of 40, the sample mean was 45. So the next part in the calculator is the sample standard deviation. It doesn't look like they gave it to us, so let's go ahead and assume the sample standard deviation is 2 yards. And so we can put 2 into the calculator. The sample size that they gave us was 20 throws. And this is a right tail test, so you go to the greater than symbol. I like blue, and then I'm going to go ahead and drag this picture in so we could see what we did. And then go ahead and calculate. And so let me drag this over as well. Okay, so in the p-value approach, you would, with a mean, you would just follow the directions. And again, if the p-value is in that critical region, right, we would reject the null. And again, I just want to emphasize what the p-value means. It says if we took another sample, what are the chances we would get the same results? If that chance is smaller than a type 1, is smaller than making a type 1 error, then we say that's statistically significant. There's no more status quo. There's some sort of change, right? And if the probability of grabbing a random sample and the probability is larger than making a type 1 error, then it's saying, hey, you know what? The chances of making a type 1 error are pretty small here in the status quo. There's no statistical significance here. So, and that's what we're looking for. So here, let's go ahead and write this out. So the p-value from the calculator go ahead, is right here. And so the p-value here is really, really small. Let me do it here. So 0.000000004. Because it has e to the negative 10. And then we compare it to the alpha, which is 0.05, right? So in this case, is alpha going to be larger or smaller, or p-value will be larger or smaller, right? And just look at it in the critical region. If alpha is 0.05, and this is a lot smaller than that, obviously it would be less than, right? Right, so if it is less than the alpha, that means the p-value lies somewhere in the critical region, meaning that if I took another random sample of Marco's throws and I would find the sample statistics and test the hypothesis, I would get something different. And that means that it's statistically significant, and then we have to reject the null. So we have to reject the null. So if we reject the null, let's come up here. We reject the null, meaning we accept the alternative. Alternative was the claim, so therefore there's enough evidence to support the blah, 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 blah. Right? So that's why crossing it out and circling what we're accepting is really important, because it'll help us with our interpretation. So our math, right, our actual numerical math tells us if we reject the null or not. However, in conversation, we discuss it as in terms of the claim. So that's why we interpret in terms of the claim. However, mathematically, we determine by rejecting or not rejecting the null. So it's important that we keep organized as best as possible. And so after that, we can just go ahead and interpret the results. So now in step 5, we would interpret the results here. So the results would be there is enough evidence to support the claim that Marco's throws have an average more than 40 yards. Okay, so this is the process. Let's go through it. So the first we're going to do is read everything, and we'll have to do preliminaries, right? The hypothesis test, we set up the null alternative, mark the claim. Determine the approach you want to use. I encourage you to use the p-value, right? And then go to the calculator. If it's about a mean, you'll use t-test. If it's about a proportion, you use 1-prop-z-test. Grab the results and go ahead and compare the p-value with the alpha, determine if it's statistically significant, and then interpret. So here, this would be statistically significant. Okay, and essentially what the results give us here is they give us a lot here. So if I went back to the calculator, let's take a look. So I just skipped over everything, right, and just went straight to the p-value. However, notice this t here. This t here is 11.18. So that was the test statistic. So the test statistic over here is the p-value, and then also the test statistic, which is t. So this means that t sub alpha was greater than the test statistic, right? So the test statistic lied in the critical region. That's approach, the classical approach, is you instead of looking at it as p-value and alpha, it's the same approach of looking at it as the t-score sub alpha and t. And so that's what these values are in the calculator. So it tells you the alternative, it gives you the test statistic, it gives you the p-value. So here is the test, here's the alternative test statistic, and this is the p-value, and then there's the sample statistics that we had.